Thank you for visiting Annie Electronics. In our last episode, we discussed the basis for the selection of the electrical components in LC filters. The DC output of the filter needs to be regulated as we discussed in episode 6, which is PN junction diode rectifier. In this episode we'll try to find out what a regulator is and what its characteristics are. To begin with, let us explain what a regulator is. Regulators keep a constant output voltage regardless of how much current is flowing through them. It is time for us to review our learning. The PN junction diode's reverse bias characteristics have now been fully understood by us. Could you please suggest anything based on the graph? Pay close attention to the graph stages. Is it not in line with the requirements of a regulator? As the current increases, the voltage nearly stays the same. However, the voltage is not entirely constant. Therefore, it cannot be used as a regulator. The reason is very simple. From the junction voltage equation, we can derive that the width of the barrier potential is inversely proportional to the doping concentration. As a result, a normal PN junction diode will have a wide width. In this interpretation, fewer charge carriers cross the junction and produce less current, and the voltage cannot be constant for the small flow of current. Using a heavily doped diode can overcome the issue, as a higher doping concentration allows more charge carriers to pass through the narrow depletion region. In this case, the much charge carrier can contribute much current, resulting in a sharp increase in current. At the same time, the voltage stays the same regardless of the current increase. Zener diodes have properties of this type. Because of this reason, Zener diodes are heavily doped, which is why they are used in voltage regulators. Let us now understand something more about Zener diode. Previously, we learned about the breakdown voltage of a PN junction diode. In a PN junction diode, the breakdown voltage limits the reverse voltage at which it can survive before it is destroyed. The reverse minority carrier current has been observed during reverse bias conditions. Increased reverse bias voltage causes the minority carriers to move rapidly and for some amount of energy to be gained. Minority carriers collide with the crystal's atoms while moving fast. When minority carriers have enough energy, they can move out valence electrons. This results in free electrons. Therefore, the newly formed minority carriers combine with existing minority carriers in order to collide with other atoms and knock out the valence electrons. In the beginning, there was one electron, but upon collision, two electrons emerged. The free electrons accelerate and displace another two valence electrons from the atoms, creating a total of 4 free electrons, and the process continues until the reverse current is enormous. This is known as avalanche effect. The avalanche effect causes the diode to conduct heavily due to the sudden appearance of minority carriers in the depletion region. Signal and rectifier diodes aren't intentionally doped heavily, so they can be operated in the breakdown region, which may damage them. With a Zener diode, the breakdown voltages can vary from 2 volts to 1000 volts depending on the doping concentration. As we just learned, Zener diodes have a narrow depletion region because they are heavily doped. As a consequence, we can see that the electric field strength, which is voltage divided by distance, is very high across the depletion region. In experiments, scientists have found that a field strength of more than approximately 300,000 volts/centimeter can displace electrons from their valence orbits. In this process, free electrons are created by a process called high field emission or Zener effect. Zener diodes can operate with ease in 3 regions: forward, leakage, and breakdown. In the forward region, after crossing the knee voltage, for CMA diode the knee voltage is 0.7 V, the diode can start conducting. The Zener diode maintains a constant output voltage regardless of the current through it. For this to occur, the source voltage must exceed the breakdown voltage of the Zener. Therefore, the current passing through the Zener diode should be less than the maximum allowable current set by the manufacturer. As a result, a series resistor is always used to protect the Zener diode. As a voltage regulator, Zener diode meets the condition that the output voltage is constant with changes in current, regardless of whether it increases or decreases. This type of circuit is also called a Zener voltage regulator or Zener regulator. A Zener diode can also be used to construct a variety of other essential electronic circuits. For example, it can be used as a pre-regulator or wave shaper, etc. The first Zener diode drives the second Zener diode in this pre-regulator circuit. This type of circuit works by providing the second Zener diode with a well-regulated input voltage from the first Zener diode so that the final output voltage is fine-tuned. A back-to-back connected Zener diode is used in wave shaping. The circuit is very simple to understand. As the positive half cycle emerges from the source, Z1 will conduct and Z2 will break down, causing a sharp rise in voltage in the positive direction. If the diode is made of silicon, the forward bias voltage will be 0.7 volts. Its output voltage will be the breakdown voltage of the Zener plus 0.7 volts. As Z2 conducts during the negative half cycle, it will be in forward bias, and Z1 will be in a breakdown region. The output voltage will be minus 0.7 volts minus Zener breakdown voltage during this time. By doing so, we can almost get a square wave. On the upcoming video, we will discuss several other types of diodes if we have the time. On our next video, we will discuss a slightly more complex topic, the switching characteristics of PN junction diodes.